This is Algebra 2 with trig, 2b.5a. We're factoring and solving polynomial equations. When factoring, always look for a GCF, greatest common factor. You've got to pull that out first, typically to make numbers easier, or in some cases just to do it. Then continue to factor completely until each polynomial cannot be factored further. You can't stop after one set of factors. You've got to factor it completely. So here, we would consider this not factorable, except that it has the GCF. And by taking the y out, you have a y in every term. We factored the y out. That drops the degree down by 1 on each of them. Now, this trinomial is factorable. You're looking for two numbers that multiply to be 12 and add to be 4. 2 and 6 multiply to be 12, but their signs have to be different. To add to be negative 12, you need a negative 6 and a positive 2. That adds to be negative 4 and multiplies to be negative 12. The next one we can factor, we see a 3 can divide into each one of those numbers. That means it's a GCF and it can be pulled out, factored out. Also, there is an x. You always look for the lowest degree to see what the maximum amount you can bring out. That leaves us with an x squared plus a 10x plus a 25. And now maybe this is factorable. And we notice that x times x would FOIL to be x squared. And 5 times 5 makes 25. And 5 plus 5 makes 10. Adds to be 10. So a better way to write it would be x plus 5 quantity squared. So here we have 5g cubed. 5 can go into both of those, 5 and 80. And the smallest exponent is g cubed, so that's the maximum amount you can factor out as a GCF. So that leaves us with g squared minus 16. Now we look at this, and it's different than the trinomials we had, but it is the difference of two squares. So the difference of two squares would be g times g. That would FOIL to make g squared. Two middle terms to cross out, so the numbers have to be the same, which would be 4 times 4. A positive and negative, when added together, would give you 0, but multiply to be 16. Now, these are all past factorings that we've done before. Now we're going to look into a special pattern. Pretty much you just need to memorize this pattern. This one here would be the sum of two cubes. Because you're adding two perfect cubes together. Essentially what we're going to do is take the cubed root of both of those. So the cubed root of a cubed would be a, cubed root of b cubed would be b. Then you square the a term, you multiply the a and the b together and change the sign, and then square your b term. And that's the same pattern as it would be for the difference of two cubes. And that would be a minus b, because they're minus, it's a difference. This has to be a minus. You square the a, you multiply the a and the b, but you change the sign. You don't make it be negative, it's got to be a positive, because when you multiply it through, it's got to cross everything out to make the middle term 0. And if you would distribute this in there twice, you would see that you would get a cubed. The rest would cross out, and you'd get b cubed at the end. Looking for perfect cubes. 1 cubed is 1. 2 cubed is 8. 27. 64. 125. 5 times 5 is 25. Times another 5 is 125. 216. 343. 512. 64 times 8 is 512. And 10 times 10 times 10 is 1,000. So now we move up and we look at w cubed minus 27. We're going to factor this completely. Notice that this is the difference of two cubes. So you're looking for an A term, and you're looking for what number that's being cubed. And we look over here and we see that 3 cubed is 27. So if you make yourself familiar with these perfect cubes, it makes factoring perfect cubes a lot easier. So your A term is W, your B term is the 3. It's not the 27. You've got to take the cubed root of 27. So now you square it, you multiply the two numbers together and change the sign and square the B term. We see that 27 is a perfect cube. We see that 125 is a perfect cube. And there is no GCF inside this. So we know that 3x being cubed makes 27x cubed. And 5 being cubed makes 125. Usually people won't write this particular step, but I'm trying to show you where the 27 comes from. Why is the A term 3x? Because when you cube 3x, you get 27x cubed. So the A term and the B term, you square the A term. Now to square the A term, you've got to square the whole thing. That's 9x squared. You can't just write 3x and put a square next to it. It's got to be squaring the entire A term. So 9x squared, multiply the two numbers together, change the sign, and then square your B term. Something to notice up here, it's a pattern that goes with all the signs. S O A P. S-O-A-P, soap. That helps remind us that the sign is the same. S stands for same. The O stands for opposite. And the AP is always positive. Same sign, opposite sign, and always positive. So if you're having troubles remembering your signs. Now, when we are factoring here, we want to bring the negative out as your GCF. Notice that both numbers are even, so you know you can bring out a 2. D squared is your lowest exponent, so you can pull that out. So then you're left with D cubed minus 125. And 125 was a perfect cube. So this is going to be D minus 5, D squared, multiply the two numbers together, change the sign, and square it. You could multiply this back together and you should be able to produce what you started with. You know that 16 is not a perfect cube. 686 isn't a perfect cube. It doesn't fall in our chart here. So when we pull out they're both even, so let's start with that. B squared is your smaller exponent. That gives us 8. Well, that is a perfect cube. B to the 5th plus 343. Well, we've heard that to be a perfect cube. So we get 2b squared. Now when you take the cubed root, let me see, that says a 5 there, right? But shouldn't it be, when you multiply, it would need to be a 3 to make 5. B squared, b cubed would multiply together to be b to the 5th. So that needs to be a 3. So 2b would be the cubed root of that. 7 would be the cubed root of that. So square it. You've got to square the 2 also. Square the 2, square the b. Minus 14b plus 49. So that's using the special pattern of the sum and difference of two cubes. Sometimes when you see a polynomial with 4 terms, you can factor it by grouping. And this is sometimes. It's not always factorable. A cubic could have up to 4 terms. A term with a 3, a 2, a 1, and none. Okay, and then this helps us out with the rest of them. First, we're going to circle our 2 groups. It's called factor by grouping, so we're going to group our 2 terms together. We factor out what we can. So I see that a 9 goes into both of those, and h squared is your smaller exponent. So that leaves me with a 3h plus 5, because 9 times 3 is 27. H squared and h is h cubed. 9 times 5 is 45. H squared and nothing is h squared. So bring down this sign. Nothing can be factored out of 5 and a 3. So you have to hold the place value. You can always factor a 1 out. In this case, it's a negative 1. So negative 1 times 3 is negative 3. Negative 1 times a positive 5 makes a negative 5. So that has to change the sign since you factored out a negative. Now notice the parentheses. They're exactly the same. They need to be the same. So these are our coefficients. The coefficients come down to make one factor. And the common factor is going to be the second factor. Now, what we talked about earlier is that you have to factor completely. Sometimes this is tough to see, but these are both square rootable. These are both perfect squares. So this is the difference of 2 squares. So take the square root, which is 3h and 3h. That makes 9h squared. A positive 1 and a negative 1 would multiply together. So you have 9h squared, negative 3h, positive 3h, cross out to be 0, and then 1 and 1 makes 1. And then don't forget your last term. It's got to be 3 h's there to make a cube. So here we're going to factor out the square. It's going to leave us with a y minus 3. Bring down your sign. Factor out the 16. That leaves us with the y minus a 3. Bring down your y squared. Bring down your 16. Now a lot of people look at this and they think that the sum of two squares is factorable, but the sum of two squares is not factorable. There is nothing that multiplies to be this. Y plus 4 does not actually make this. And of course, y plus 4, y minus 4 doesn't make this either. So that is completely factored. Now previously, we have factored x squareds when they're in the first term, and the factors look like x plus a number and x plus another number. Often it's minus, but it all depends on what your numbers are. So when we factor the polynomials x to the fourth, we've never factored x to the fourth. We don't have any special rules for x to the fourth. So we're just going to factor like they're x squareds. But to get x to the fourth, we have to have squares. So x squared and x squared makes x to the fourth. X squared plus an x squared gives you an x squared number in the middle, and then your constant. You can even do it with larger exponents. You just got to take half of those. So x to the third and x to the third would be able to multiply to be x to the sixth. So let's take a look here. First of all, we notice there's a GCF, and I have m in all of these, actually an m squared is my smallest exponent. That's going to leave me m to the 10th plus 17m to the 5th. Notice that this is half that size. It's always going to be half that size if it's following this pattern. And this is actually 18. Three goes into 5 one time. With 2 left over, 3 goes into 24 8 times. This is your 17. 3 times 17 makes 51. Now this is factorable. How do we make m to the 10th? Well, if it was 5 and 5, when we foiled that together, we would multiply and add the exponents. To multiply to be 17, we need 17 and 1, and that would add to be 18. They'd both need to be positive. Neither of those are factored any further. Look at this one. First of all, we think, is this the difference of two cubes? But this is a 4, so it's not cubes. Could it possibly be the difference of two squares? If this was a 2, that's square rootable, that's square root. So let's look at it as 4g squared squared. If you square the 4, you get 16. And if you square g squared, you get g to the 4th. That means that this number, 25 times 25, makes 625. So I was able to take the square root of both of those, and this is my a and my b. So I've got 4g squared minus 25 and 4g squared plus 25. This is factorable. 2g plus 5, 2g minus 5. So here we saw that this was the difference of two squares, so I factored it apart. 2 times 2 makes 4, g and g makes g squared. Negative 10 and positive 10 give you 0 in the middle, and 25. This here is not factorable. This is the sum of two squares, but sum of the two squares cannot be factored. Here we have a 10 that can be factored out. And just like we talked about before, we're going to treat this just like it was an x and an x, but we're going to call it x squared and x squared to add up to 4. And it would still be 1 and plus 1 because that multiplies to be negative 1, gives us 0 in the middle, and multiplies to be x to the 4th. Here's the difference of two squares again. Remember, you've got to keep looking for x times x gives you x squared, negative and positive gives you 0 in the middle, negative 1. Alright, here we're going to be doing the same thing, but now we're going to find the actual zeros. So if your function equals 0, that's the first thing you need to do, is move everything over to the same side of the equal sign. This is the 5th power. We don't factor to the 5th power with special rules. We've got to use one of our current rules. So if you notice, there's a GCF that's in all of this. So that was the hint that something else had to have been done. So we have x to the 4th minus 10x squared plus 9. Now we have a 4, which we don't factor either. With a special rule, we're going to treat that, and it has the pattern of 4, 2. So it's half the amount. So if we have an even exponent with half the amount, we can treat this one just like it was an x and an x. Right? That would be a negative 9 and negative 1. But we need x to the 4th. We need it to add to be x squared. So we need these to be squares. X squared and x squared gives you x to the 4th. Negative 1 and a negative 9 adds to be negative 10 and multiplies to be positive 9. Don't forget to bring down your 4x. So since this equals 0, we can keep the 0 coming all the way through. Now, this is the difference of two squares. X and x makes x squared. 3 and 3 makes 9. Plus and minus. And the same thing goes on here. So we set the 4x equal to 0, the x plus 3 equal to 0, so when you divide by 4, you get x equals 0, subtract the 3 to get negative 3, add the 3 to get 3, add the 1 to get 1, subtract the 1 to get negative 1. So notice we have 1, 2, 3, 4, 5 terms. Because this was 5th degree, we're going to have up to 5 terms. Sometimes it might be a repeat of the same term, so that's called a double zero. But in this case, they're all separate. They're all separate zeros on the graph. So the largest exponent is x to the 5th. Then we'd bring over the 14x cubed, and we'd finish it off with the smallest exponent to the 1st power. Now we look for some GCFs. That's x to the 4th minus 7x squared plus 12. Again, we see the pattern of 4 and 2. It's half the even power. So we can treat this just like it was a factoring we've done before with a quadratic. We're going to use a 3 and a 4. It's got to be a negative and a negative to make a positive when multiplying, and negatives when you're adding them together. But to get the 4, they both have to be squared. Don't forget to bring down your x squared. You have 2x. You have x squared minus 3, and this is actually the difference of two squares again, so we want to factor it completely. So we set our 2x equal to 0, our x squared minus 3 equal to 0, x minus 2, and x plus 2. Well, of course, that makes 0. When we add the 3 to the other side, and we take the square root of that, we're going to get plus or minus the square root of 3. Add the 2 across, subtract the 2 across. So just to check our work, to be sure things were set up right, we factored the 2 out of each one of these. So they gave us 7, gave us 12, signs are correct. Multiplies and adds, add it over,